The most complicated machine human beings have ever built sits in a 27-kilometre ring under the border of France and Switzerland, cooled colder than deep space, and at full power it can resolve a distance about 60,000 times smaller than a proton. That is the current edge of human sight. Everything we have ever seen, measured, or confirmed sits above it. The Planck length is 15 orders of magnitude below that. Sit with a proportion for a second. The gap between the smallest thing we have ever seen and the place where physics stops is slightly larger than the gap between the width of a human hair and the orbit of Neptune. We built the ring to reach the hair. And that is the floor of tonight's story, not the ceiling, because when you follow the descent all the way down, you find a Soviet physicist who worked out what was waiting there in 1936 and was shot at 31 before anyone read it. You find a single fraction published in 1986 that killed an entire branch of theoretical physics. You find a laboratory at Fermilab that went looking for the graininess of space with 240-meter lasers and came back with silence. And you find a small number of people who now think the reason we cannot reach the bottom is that there is no bottom, and that distance itself is a statistic, in the same way temperature is a statistic. Get comfortable, stay to the end, because by the time we get there, the gap between your hand and whatever it is resting on is going to stop looking like a property of the world. If you want these without ads, that is over on our Patreon, Meridian Labs, which this channel is part of. Ad-free episodes across every channel in the group, early access before they go public, and an audio-only feed for listening with the screen off. Subscribe or join if you haven't. Let's ease into it. Push a microscope far enough and it stops being a microscope. It becomes a black hole. That is not a metaphor, and it is not a thought experiment that fell apart under scrutiny. It is the most robust result in the whole of quantum gravity. And it is the reason there is a flaw to how closely anything in this universe can ever be examined. The flaw is not a limit of our instruments. We are not waiting for better lenses, or brighter beams, or a bigger accelerator. The flaw is a limit of looking itself, written into the relationship between three constants that were fixed before there was anyone here to measure them. Here is the mechanism, and it is almost offensively simple. To see something small, you need a probe with a short wavelength. Short wavelength means high momentum. High momentum means high energy. So the smaller the thing you want to resolve, the more energy you have to concentrate into the region where it sits. That is fine for a while. That is how every microscope and every particle collider ever built has worked. But energy gravitates. Energy curves space exactly the way mass does, and if you concentrate enough of it into a small enough volume, the region collapses. It closes over. It forms an event horizon around the very thing you are trying to look at, and the information you wanted comes back to you as featureless thermal radiation, if it comes back at all. There is a specific distance at which this becomes unavoidable. It is called the Planck length, and the currently recommended value, from the 2022 adjustment of the fundamental physical constants, is 1.61625 times 10 to the negative 35th of a meter. Every attempt to look closer than that fails in the same way, not because the apparatus is imperfect, because the act of concentrating enough energy to resolve that distance creates a black hole whose horizon is larger than the distance you were trying to resolve. Space, at that scale, behaves less like a stage and more like something that closes its eyes when you get too near. I want to be careful with that last sentence, because it is the kind of sentence that gets a physics channel deservedly torn apart in the comments. Nobody is claiming the universe has intentions. What I am saying is narrower and, I think, stranger, the mathematics that describes measurement and the mathematics that describes gravity. Two completely independent frameworks built by different people for different reasons. Converge on the same number and hand you the same answer at that number, and the answer is a refusal. Ask for smaller, and the theory does not give you a wrong result. It gives you no result. It stops producing numbers. Now hold that, because there is a second fact about the Planck scale that almost nobody outside the field knows, and when you learn it, the whole picture becomes considerably weirder. The Planck length is absurdly small. The Planck time, which is how long light takes to cross it, is 5.39124, 7 times 10 to the negative 44th of a second, and there is no meaningful comparison I can give you for that duration that will land, because there is nothing in human experience within 30 orders of magnitude of it. The Planck temperature is 1.416784 times 10 to the 32nd Kelvin, which is hotter than anything that has existed since the first instant of the universe. And the Planck mass is about 21.8 micrograms. That is not a subatomic quantity. That is a speck. It is roughly the mass of a flea's egg, or a very small grain of sand, or about a 40th of a raindrop. It is a thing you could, in principle, put on the tip of your finger and on a good day with good light, actually see. The fundamental unit of mass in the theory that describes the end of physics is a visible object. Nobody knows why. That asymmetry, the fact that the natural units of length and time and temperature run off toward the unreachable in one direction, while the natural unit of mass sits down casually at human scale, is one of the oldest unexplained features of theoretical physics, and it is usually mentioned in a single parenthetical sentence in graduate textbooks, and then dropped. It is called the hierarchy problem when it is dressed up formally, and it has resisted every attempt at solution for half a century. The reason the Planck mass is the size of a flea's egg rather than the size of a proton is that gravity is stupefyingly weak compared to every other force, by a factor of around 10 to the 38th, and nobody can tell you why that number is that number. But this is where I need to make you a promise about the shape of the next 2 hours, because the thing I have just described is the version of the Planck scale you can find on any physics blog. The floor, the pixel, the smallest possible distance that reality is allowed to have. That version is repeated everywhere, and it is, in a way that I think should genuinely annoy you once you understand it. Wrong. The Planck length has never been measured. It has never been probed. Nothing in the history of experimental physics has come within 15 orders of magnitude of it. Every claim you have heard that the universe is pixelated at that scale, that space is made of tiny discrete chunks, that reality has a resolution, is an extrapolation from theories that have produced no confirmed prediction. Some of the best constructed experiments ever built have gone looking for exactly that graininess and have come back with nothing. So the central question I want to hold open for the whole of this, the one I do not think has an answer yet and may not have an answer in our lifetimes, is not what is the smallest distance. That question invites a number, and a number would let you leave. The question is worse than that. The question is whether the word distance means anything at all down there. Not whether we can measure it. Whether it refers to something. Because there is a growing, and I think, badly undercommunicated body of work suggesting that the reason our theories break at the Planck scale is not that they hit a wall. It is that they were never describing a thing in the first place. That distance and duration, and the smooth continuum of points you were shown on a blackboard when you were 15, might be a large-scale average of something else entirely. A statistic. A property that only exists when you have enough of something, the way temperature only exists when you have enough molecules. Hold on to that word. Temperature. I am going to leave it there and not touch it again for a long time, and when it comes back at the end of this, it is going to mean something that I still, personally, have not found a comfortable way to think about. Because here is what makes this story different from most of the unsolved problems in physics. Most open problems are open because the data is missing. We do not know what dark matter is because we have not caught any. That is a normal scientific situation. It is frustrating, but it is legible. You build a better detector and you wait. The Planck scale is not that. We have known since the 1930s, and we have known rigorously since the 1980s, that the two most successful theories in the history of science are not merely incomplete at that scale, they are mathematically incompatible with each other there, in a way that has been proven, published, and confirmed by independent calculation. The failure is not a gap. It is a demonstrated impossibility, and I will show you the exact paper and the exact coefficient where the corpse was nailed into the coffin. And in the roughly 90 years since the first person noticed that this was going to happen, and I will tell you what that man's government did to him, no proposed replacement has produced a single verified experimental prediction. Not one. Loop quantum gravity, string theory, causal set theory, causal dynamical triangulations, asymptotic safety, all of them, every one, has produced zero confirmed novel predictions in the domain they were built for. That is not a criticism of the people doing the work. Some of them are among the sharpest thinkers alive, and they are attacking a problem where the relevant energy scale is about a quadrillion times higher than anything we can build a machine to reach. Nobody is loafing. But it does mean something specific about the epistemic situation, and it is something the popular presentation of this subject systematically obscures. When a documentary tells you that space is made of loops, or that reality is a network of causal atoms, what is actually being communicated is that a mathematically consistent structure exists on paper which has so far told us nothing new about the world that we could go and check. The confidence in the presentation is not coming from the evidence, it is coming from the presentation. And I want to be equally hard on the other direction, because it would be easy to turn this into a 2-hour complaint about theorists, and that would be lazy, and it would also be false. The physics I am going to walk you through is real, published, and in several places genuinely magnificent. The reason the field looks the way it does is not cowardice or careerism, though we will get to a few episodes where it was clearly both. It is that the object of study has arranged itself to be unobservable, and the honest response to that is either to work anyway on very thin threads of evidence, or to work on something else. Nearly everyone chose something else. The ones who stayed are working in the dark on purpose. But that leaves you sitting there having clicked on a video about what is below the Planck length, in a strange position that I want to name explicitly before we go any further. You are not about to be told the answer. There is no answer. What you are about to be told is how a physical theory dies, what it looks like from the inside when a description of reality stops describing anything, and what a small number of people think is standing behind the wreckage. And the first thing to understand about that wall is that we walked into it entirely by accident more than 120 years ago, before quantum mechanics existed, before relativity existed, before anybody had confirmed that atoms were real. The number was written down in 1899. The physics that explains why it matters would not arrive for another 60 years, and the man who wrote it down had no idea what he had found, which did not stop him from making a claim about it so grandiose that reading it now, knowing what happened to him afterwards, is genuinely difficult. In May of 1899, Max Planck presented a paper to the Prussian Academy of Sciences in Berlin. It was the last in a series of 5 reports, with the collective title translated of On Irreversible Radiation Processes. The series was mostly about thermodynamics, and it was mostly a failure, in the sense that the central argument Planck was trying to make about the irreversibility of radiation did not survive contact with his critics. But at the very end, in the final section, numbered 26, under a heading he wrote himself as natural units of measure. He did something that had nothing to do with the rest of the paper. He noticed that if you take the speed of light and the gravitational constant and a new constant of his own that he had introduced earlier in the same work and labelled B, you can combine them in exactly one way that gives you a length. exactly one way that gives you a mass, exactly one way that gives you a time, and exactly one way that gives you a temperature. The dimensions only fit together one way. There is no freedom in it. Given those three numbers, the units fall out of the algebra like a lock opening. And then Planck wrote a sentence about them that I want to give you in full, because it is one of the most astonishing pieces of overreach in the history of physics, and it turned out to be correct. He said that these units retain their meaning, and I am translating directly, for all times and for all civilizations, including extraterrestrial and non-human ones, and can therefore be designated natural units of measure. Consider where he was standing when he wrote that. It was 1899. The electron had been identified 2 years earlier, and its nature was still argued about. Ludwig Boltzmann was still fighting a losing public battle to convince a substantial fraction of German-speaking physics that atoms existed at all, a fight that would contribute to his suicide 7 years later. There was no quantum theory. Planck's own constant, the one he was calling B, would not acquire its meaning as the quantum of action until December of 1900, 18 months after this paper, and Planck himself would spend the following decade trying to explain it away. Special relativity was 6 years in the future. General relativity, which is where the gravitational constant acquires its real significance, was 16 years away. He had no theory that made those three constants belong in the same equation. He combined them because they were the only universal constants he could find, and the dimensions worked. And every serious attempt at a quantum theory of gravity since, built on frameworks he could not have conceived of, using mathematics that did not exist, arrives at the same length. String theory arrives at it. Loop quantum gravity arrives at it. Causal set theory arrives at it. The black hole argument I opened with, which requires general relativity and quantum mechanics and neither existed, arrives at it. A man who did not believe that energy came in discrete packets, and who would later describe his own discovery that it does as an act of desperation, wrote down the address where physics ends, and then went back to worrying about entropy. Arthur Eddington, who was one of the very few people paying attention, said in 1918 that this length must play some part in any complete interpretation of gravitation. Then the observation sat almost untouched for another 40 years. But Planck was not first, and this is the part of the story that gets amputated from every popular retelling, including, I will admit, several I have made myself before I went and checked. 25 years earlier, in August of 1874, an Irish physicist named George Johnston Stoney read a paper at the British Association meeting in Belfast, in which he did exactly the same thing. He took the speed of light, and the gravitational constant, and the charge on a single unit of electricity, and he built a natural system of units out of them. He read the paper again to the Royal Dublin Society on the 16th of February, 1881, and published it in the philosophical magazine that May. The Stoney length is about 1.38 times 10 to the negative 36th of a metre. That is not the Planck length. It is smaller by a factor of about 11.7, because Stoney normalised the electric charge where Planck normalised the quantum of action, and the ratio between the two is the square root of the fine structure constant. But conceptually, it is the same move. It is the same insight. Build a measuring system out of the universe instead of out of the human body. Stoney had it a quarter of a century earlier. Stoney is also the man who coined the word electron. He called it an electrolion in 1881 and shortened it later, and he meant it as the name for the fundamental unit of charge, which he had correctly deduced must exist and must be quantist, more than 15 years before J.J. Thomson identified the particle that carries it. In 1894, he had to write to the Philosophical Magazine to defend his claim to the word against Helmholtz, and against a German physicist named Hermann Ebert, who were using it without attribution. His estimate of the size of the charge was wrong. He put it at about a 16th of the true value, because he was working from a bad figure for the number of molecules in a cubic millimetre of gas. Some sources say the error was closer to a factor of 20. I have not been able to resolve that discrepancy, and I am telling you it exists, rather than picking the one that sounds tidier. But he named the electron, he was right that charge is quantist, and he built the first natural unit system in history. And the units are called Planck units. There is a footnote in the literature called the Stoney units, and essentially nobody uses them. This is not a scandal. Nobody suppressed George Johnstone Stoney. He was a respected figure, secretary of the Royal Dublin Society, moving in the same circles as Kelvin and Maxwell. What happened to him is more ordinary, and I think more instructive about how physics actually works. The units that survived were the ones attached to the constant that turned out to matter. And the constant that turned out to matter was Planck's. And so Stoney's version was quietly dropped and the story got simplified to one name. The history of science is not usually a record of what was discovered first. It is a record of what was discovered by whoever the subsequent theory made important. Remember that mechanism. It is going to come back in a far uglier form in about 40 minutes. Now, if you have been listening carefully to the numbers I gave you at the start, you may have noticed something odd about the way I quoted them. I said the Planck length is 1.61625 5 times 10 to the negative 35th of a metre, and then I stopped. I did not tell you the uncertainty. The uncertainty on the last two digits is about 18 parts in the 10th decimal place, which sounds fine until you ask where it comes from. Since the redefinition of the international system of units in 2019, both the speed of light and Planck's constant are exact, not measured. Defined, the speed of light is 299,792,458 meters per second, by decree with no error bar, because the metre is now defined in terms of it. Planck's constant has been fixed to an exact value in the same way, which is how the kilogram was redefined and the last physical prototype in Paris was retired. Which means that every scrap of uncertainty in the Planck length, and the Planck time, and the Planck mass, and the Planck temperature now comes from one place. It comes from big G, the gravitational constant, and big G is the worst measured fundamental constant in physics by an enormous margin. The recommended value is 6.67430 times 10 to the negative 11th, in the usual units, with a relative uncertainty of about 22 parts per million. To put that in company, the electromagnetic moment is known to about 1 part in 10 billion. The gravitational constant is known about 10 million times less precisely than that, and the reason is not that people have not tried. They have tried very hard, and this is where the story gets uncomfortable. Individual modern measurements of big G claim precisions of 11 to 40 parts per million. Their central values disagree with each other by several hundred parts per million. That is not a small mismatch. That is groups of careful, competent experimentalists using torsion balances and beam balances and atom interferometers, reporting numbers that sit far outside each other's stated error bars. The specifics are worth having. In 2000, a team led by Jens Gundlach and Stephen Merkowitz at the University of Washington published a torsion balance result in Physical Review Letters with a claimed accuracy of 14 parts per million. In 2013, a team at the International Bureau of Weights and Measures near Paris, led by Terry Quinn, published a value about 241 parts per million higher. In the mid-1990s, a group at the German National Metrology Institute published a value more than 5,000 parts per million above the accepted figure, which took years to sort out, and which nobody at the time could immediately explain. And then in 2018, a group in China led by Qing Li published 2 independent measurements in Nature, using 2 different methods, each claiming about 11.6 parts per million precision. The 2 numbers did not agree with each other. Same laboratory, same team, same year, and 2 answers that could not both be right. The authors wrote in the paper that the discrepancy of up to 0.05% in recent determinations suggests there may be undiscovered systematic errors. Now here is what the committee that recommends these values actually did about it. When the results are mutually inconsistent, you cannot just average them and quote a tiny error bar, because the error bar would be a lie. So the committee applied what is called an expansion factor. They multiplied the stated uncertainties of the input measurements by 3.9 until the disagreement between them looks statistically acceptable, and published the result. That is not fraud, and it is not even unusual. It is a standard, documented, openly described procedure, and if you read the technical report, it is right there in the text. But sit with what it means for a second. The constant that fixes the location of the boundary where physics ends is the one constant we cannot measure cleanly, and the official value is produced by taking a set of measurements that contradict each other and inflating everyone's error bars by a factor of nearly 4 until they overlap. I am not telling you the Planck length is wrong. The uncertainty from all of this is around 1 part in 100,000, which for our purposes is nothing. The wall is where we think it is. I am telling you that gravity has been resisting precise measurement at the scale of a laboratory bench in a quiet room with a lead sphere on a wire for 227 years since Cavendish, and that we are about to go and talk about what it does 35 orders of magnitude further down. Because that is the real problem, and it is time to make the distance concrete. Everyone says the Planck length is small. Almost nobody has actually walked the ladder down to it, rung by rung, to see how far away it really is. When you do, 2 things happen. The first is that you find out the gap is even more absurd than the phrase 15 orders of magnitude suggests. The second is that you find out the rungs we can already reach do not hold either. Start with a grain of sand, because sand is the only thing at human scale that has a formal definition small enough to be useful. In 1922, a geologist named Chester Wentworth published a classification of sediment in the Journal of Geology that is still the standard, and it says that a grain counts as sand if it is between 1/16 of a millimetre and 2 millimetres across. Medium sand, the stuff you would picture, is 1/4 to 1/2 millimetre. Take 1 grain, 1/2 millimetre, hold it between your fingers where you can just about feel it. Now go down by a factor of 10. You are at 50 micrometers, which is the thin end of a human hair. Hair runs between about 50 and 100 micrometers, which means a single grain of sand is roughly 5 to 10 hairs wide. Everything from here on is invisible to you, not difficult to see. Impossible. The human eye cannot resolve below about 50 micrometers no matter how good the light, because the packing of the photoreceptors on your retina imposes a flaw. You have already left the world you have direct evidence of, 1 factor of 10 in. Down again. 7 or 8 micrometers. And you are the size of a red blood cell. There are somewhere around 25 trillion of these in you right now, and every one of them is small enough that it has to deform to squeeze through the narrowest capillaries. Down again. 1 or 2 micrometers, and you are a bacterium. An E. Coli cell is about 2 micrometers long and 1/2 micrometer wide, which means you could line up roughly 250 of them across a single grain of sand. Down again, and something changes. At 100 nanometers, you are the size of an influenza virus, and viruses are the point where the objects stop being alive in any sense that survives scrutiny. There is no metabolism down here. There is only structure and chemistry. A poliovirus is about 30 nanometers across, which is small enough that the concept of an interior barely applies. Down again. Now we are at the molecule, and this is where I need to stop and correct something, because there is a number in wide circulation that is wrong, and I have seen it in places that should know better. A water molecule is not about 1/10 of a nanometer across. That figure is repeated constantly, and what it actually describes is an atomic radius, not the size of the molecule. The effective diameter of a water molecule, the number you would use if you wanted to know how many fit in a space, is about 0.275 nanometers, nearly 3 times the number you have probably been given. If you have ever seen a graphic showing how many water molecules fit across a virus, there is a reasonable chance it was off by a factor of 3, in a direction that made the universe look smaller than it is. Down again. 53 picometers and you are at the Bohr radius, the characteristic size of a hydrogen atom, 5.29 times 10 to the negative 11th of a meter. And here we cross the first genuine threshold of this descent, because the atom is where classical intuition stops working entirely. The electron does not orbit. There is no surface. What you have is a probability distribution, and the number I just gave you does not measure an edge. It marks the distance at which the electron is most likely to be found. Asking how big a hydrogen atom is already requires you to specify what you mean by size, and different definitions give different answers. That is worth flagging now, because it is the first appearance of a pattern that gets steadily worse all the way down. The deeper you go, the more the word size stops being a property of the object and starts being a property of how you asked. Down again, and now, in one jump, the biggest empty space in ordinary matter. From the atom to the nucleus is a factor of about 100,000. If you scaled a hydrogen atom up until it was the size of a football stadium, the proton at the center would be a grain of rice on the center spot, and everything else, the entire volume of the stadium, is the region where an electron might be found. Ordinary matter is essentially vacuum with rules, and I have to stop on the word vacuum for a moment, because I have used it casually and it is the single most dishonest word in physics. The empty space inside an atom is not empty. According to quantum field theory, which is the most accurately tested framework human beings have ever produced, what we call empty space is a set of fields extending everywhere, and every one of those fields has a lowest possible energy state, which is not zero. Each mode of each field carries a residual half quantum of energy that cannot be removed, because removing it would mean specifying both the field value and its rate of change exactly, and the uncertainty principle forbids that. So the vacuum has an energy density, and you can calculate it. You add up the contribution from every mode of every field, and because there are more modes available at shorter wavelengths, the sum is dominated by the very shortest wavelengths you allow, which means the answer depends entirely on where you stop counting. And the natural place to stop counting, the only physically motivated cutoff anybody can name, is the Planck length. Below that, the modes are meaningless, because that is where the theory ends. So you do the calculation with the Planck cutoff, and you compare it to the vacuum energy density we actually observe, which we know because it drives the accelerating expansion of the universe and has been measured by supernovae and by the cosmic microwave background. The prediction is too large by a factor of about 10 to the 120. That is not a typographical error, and I am not exaggerating for effect. 120 orders of magnitude. It is generally described correctly as the worst quantitative prediction in the history of science. There is no competition for that title. Nothing else is close. The second worst failure in physics is a rounding error next to it. There is a sourcing dispute worth knowing about, which is that if you refuse to trust the theory all the way to the Planck scale and stop at the electroweak scale instead, where we have actually done experiments, the discrepancy shrinks to around 60 orders of magnitude, 60 rather than 120. Some authors quote one figure, and some quote the other, and the difference between them is entirely a difference of opinion about how far down you are willing to believe the mathematics. I will give you both and let you decide which is more embarrassing. Now notice something about the structure of that failure, because it is not incidental to this story. It is this story. The largest error in the history of physics is produced by taking a calculation and running it down to the Planck length. The size of the error is set by exactly the boundary we are discussing. If you stop earlier, the error is smaller. The magnitude of our single greatest failure is a direct measurement of how much we are wrong about what happens at the bottom. That is a genuinely strange situation to be in. It means we have, sitting in the open, in every graduate textbook, a number that quantifies our ignorance of the Planck scale, and the number is 120 orders of magnitude, and the standard response to it is to note that it is an unsolved problem and move to the next chapter. I want to be fair about why. There is no known way to fix it. Supersymmetry was supposed to cancel most of it, and the Large Hadron Collider has now spent 15 years failing to find supersymmetry at the energies where it would have helped. Anthropic arguments have been offered and are unfalsifiable. Every proposal on the table either does not work or cannot be tested. The reason nobody talks about it is not that anybody is hiding it. It is that there is nothing to say, and a field with nothing to say about its own largest failure tends, in practice, to talk about other things. But if you have ever wondered whether physicists are quietly confident that they understand the small-scale structure of reality and are simply working out the details, hold that number in your head, 120 orders of magnitude, on the most basic question you can ask about what empty space weighs, in the most successful theoretical framework ever constructed. Keep going down. The proton itself has a radius of roughly 0.84 femtometers, and I want to spend a moment on that number, because it is the single most embarrassing measurement in modern physics, and it tells you something important about how far we can actually be trusted. For decades, the proton radius was measured two ways. You could fire electrons at hydrogen and measure how they scattered, or you could do precision spectroscopy on hydrogen atoms and infer the size from the way the proton's finite extent shifts the energy levels. Both methods agreed. The accepted value going into 2010 was about 0.8768 femtometers, with an uncertainty in the third decimal place. Then a team led by Randolph Pohl did something clever. They made muonic hydrogen. A muon is a heavy electron, about 200 times the mass, which means it orbits about 200 times closer to the proton, which means it spends far more of its time inside the proton, which means it is a vastly more sensitive probe of the proton's size. In July of 2010, in Nature, they published their result, 0.84184 femtometers, 4% smaller. And with the precision they had achieved, that was a 5 sigma discrepancy from the accepted value on the first attempt. A refinement published in Science in 2013 tightened it further and pushed the disagreement to around 7 sigma. To be clear about what 7 sigma means, the threshold for claiming a discovery in particle physics is 5. 7 sigma is the level at which, if the two measurements were really measuring the same thing and the errors were understood. The chance of a fluctuation this large is smaller than any number you have an intuition for. Either the proton was two different sizes depending on what was orbiting it, which would mean the standard model is broken, or somebody's error analysis was wrong. For 9 years, nobody knew which. There were conferences about it. There were serious papers proposing new physics, new forces that coupled differently to muons than to electrons. And then in 2019, 2 results arrived within months of each other. A Jefferson Lab experiment called PRAD, which stands for proton radius, did electron scattering at unprecedentedly low momentum transfer and got 0.831 femtometers, agreeing with the muon. And a group at York University in Toronto, led by Eric Hessels, did the hardest possible version of the ordinary hydrogen measurement, the one that had produced the larger number for decades, and got a value agreeing with the muon as well. Randolph Pohl, who had started the whole thing, said afterwards that he did not think there was any hope left that the discrepancy was due to new physics. So the puzzle was declared solved. The small value was right. The decades of larger values had contained systematic errors that nobody had spotted. And I want to be honest with you about how solved it actually is, because the popular account stops at the word solved and the literature does not. Jan Bernauer, who led one of the major scattering experiments that had produced the large value, has said publicly that he is not entirely convinced by the PRAD analysis. A 2018 measurement from a group in Paris agreed with the larger value. The PRAD experiment, in the course of resolving the radius, introduced a new and unexplained discrepancy in the proton's form factor at low momentum transfer that is still sitting there. A review published on the preprint server as recently as 2025 states plainly that the consensus is not universally held. The phrase I would use, and I think it is defensible, is that the proton radius puzzle was quietly declared resolved rather than definitively resolved. The field moved on because the weight of evidence shifted and because staying was unrewarding. That is a normal thing for a field to do. It is also the exact mechanism that produces textbook statements which nobody has checked in 20 years. And this is the proton. This is an object we can make in quantity, hold in a magnetic bottle, fire at things, and study with a dozen independent techniques. It is 100 million times larger than anything we are about to discuss. We spent 9 years unable to agree on how wide it is. Keep descending. Below the proton are the quarks, and here the ladder stops giving you sizes and starts giving you upper limits, which is a different kind of statement. Nobody has ever measured the size of a quark or an electron, because nothing has ever shown any sign of having internal structure. What experiments give you instead is a bound. If the electron had substructure, that substructure would show up as a tiny deviation in how electrons scatter at very high energy, and the absence of that deviation lets you say the structure must be smaller than some value. The Large Electron-Positron Collider at CERN, running through the 1990s, and the subsequent work at the Large Hadron Collider, put the compositeness scale for both electrons and quarks somewhere above 10 trillion electron volts, and in the strongest channels a good deal higher. Translated into a distance, that is a bound of roughly 10 to the negative 20th of a meter or below. So let us take stock of where we are. The Large Hadron Collider, running at 13.6 trillion electron volts, probes a distance of about 1.45 times 10 to the negative 20th of a meter. That is the smallest distance any human instrument has ever resolved. It cost roughly 9 billion Swiss francs, and it required a 27-kilometer ring under the border of France and Switzerland, cooled to 1.9 Kelvin, colder than deep space, to hold the magnets superconducting. And the Planck length is 1.616 times 10 to the negative 35th of a meter. The ratio between those two numbers is about 900 trillion, roughly 15 orders of magnitude. Now, I have heard this gap described many times as being larger than everything we already understand, and I want to correct that, partly because it is wrong, and partly because I think you should always be suspicious of a channel that only ever adjusts the numbers in the direction that makes the story bigger. From the smallest thing the Large Hadron Collider can see, up to a person standing in a room, is about 20 orders of magnitude. From the collider down to the Planck length is about 15. So the unexplored territory below us is not larger than everything above us. It is somewhat smaller. The dramatic version of that comparison is an exaggeration, and it circulates widely. But 15 orders of magnitude is still a number that deserves better than the phrase very small, so here is one that checks out. The width of a human hair is about 70 microns. The diameter of the solar system, taking Neptune's orbit, is about 9 billion kilometers. The ratio between those is around 14 orders of magnitude, which means the distance between the smallest thing we have ever seen and the Planck length is in proportional terms slightly more than the distance between a human hair and the entire solar system. We have built the most complicated machine in human history to reach the hair. The Planck length is out past Neptune. And there is no path. This is the part that does not get said clearly enough. To reach the Planck energy with an accelerator using current technology, you would need a ring roughly the size of the Milky Way galaxy. That is not an engineering challenge. That is not a matter of funding or political will or waiting for better superconductors. There is no incremental improvement that closes a gap of 15 orders of magnitude in collision energy. Every experiment anyone will ever build to probe this will be indirect, will rely on astrophysical accidents, and will constrain models rather than observe the thing. So we are looking at a region of reality that is causally connected to us, that our best theories say we are made of, and that we have no mechanism, now or in any foreseeable future, to observe. Which means everything from here on rests on theory, and that would be an acceptable situation, if uncomfortable, except for one thing. The theory does not work down there. And the man who noticed that first noticed it in 1935, wrote it down in 1936, and was shot in a Leningrad prison 2 years later at the age of 31. His name was Matvei Petrovich Bronstein. He was born on the 2nd of December 1906 in Vinnytsia, in what is now Ukraine, and by his late 20s he was regarded by the people around him as one of the sharpest theoretical minds in the Soviet Union, which in the 1930s was a serious statement. He wrote children's books about science on the side. He was married to Lydia Tchaikovskaya, who would go on to become one of the most important dissident writers and human rights campaigners of the Soviet century, and whose account of that period remains one of the primary documents of what it was like to live through it. In November of 1935, he defended his doctoral thesis in Leningrad. The examining committee included Vladimir Fock and Igor Tamm, both of whom were among the finest physicists in the country, and Tamm would later share a Nobel Prize. The thesis was published the following year as a paper whose title, translated, is Quantum Theory of Weak Gravitational Fields. What Bronstein did in that paper is take a question that had been settled for electromagnetism and ask it about gravity. And the reason the answer mattered is that everyone at that point assumed gravity would work the same way. In 1933, Niels Bohr and Lon Rosenfeld had published an analysis of how precisely you can measure an electromagnetic field given quantum mechanics. The question is subtler than it looks. To measure a field, you need a test particle, something you put in the field and watch. But the test particle has its own charge, so it makes its own field, which disturbs the thing you are measuring. And it has a position and a momentum, so quantum uncertainty applies to it. Bohr and Rosenfeld worked through it in exhausting detail and found that the disturbance can always be made negligible. The trick is the ratio of charge to mass. You take a test body with a large charge and an enormous mass. The large charge makes it responsive to the field. The enormous mass makes it sluggish, so it barely moves, so its own radiation is negligible. And its quantum uncertainty in position is tiny. You can push that ratio as far as you like. There is no limit in principle. Electromagnetic fields can be measured to arbitrary precision, and quantum electrodynamics is safe. Bronstein asked what happens when you run the identical argument for the gravitational field, and the answer is that the trick does not exist. It cannot exist, because in gravity, the charge is the mass. That is the equivalence principle, the thing Einstein called the happiest thought of his life. The property that makes an object respond to gravity and the property that makes it resist being moved are the same property, which means the ratio Bohr and Rosenfeld had exploited, the ratio you have to make large in order to measure a field cleanly, is fixed at exactly 1 and can never be adjusted. There is no such thing as a heavy test body with negligible gravitational charge. There is no neutral probe for gravity. Every possible measuring device for the gravitational field is itself a source of the gravitational field, in exactly the proportion that makes it useless. Combine that with the uncertainty principle, and you get an absolute limit on how precisely any gravitational field can ever be measured at any scale by anyone using any technology. And when you push that limit to its extreme, the region of space-time you are trying to measure collapses into a black hole, and the measurement becomes meaningless. Bronstein worked all of this out in 1935 using the Planck mass, which he described in his own text, and this is his phrasing, as a dust particle weighing 1/100th of a milligram, which is the same flea's egg I opened with, seen from the other side of a century. And then he wrote the sentence that makes him, as far as I can determine, the first human being to understand what the rest of this is about. He concluded that a genuine quantum theory of gravity would require what he called the rejection of Riemannian geometry, and, he went on, perhaps also the rejection of our ordinary concepts of space and time, replacing them with some much deeper and non-evident concepts. 1936. Sit with the date. Quantum mechanics was 10 years old. General relativity was 20. The word graviton had barely been coined. There was no string theory, no loop quantum gravity, no holographic principle, no causal sets, none of the vocabulary that the rest of this is going to be conducted in. And a 29-year-old in Leningrad had already worked out that the two great theories were not going to be reconciled by making one of them more careful, that geometry itself was the thing that was going to have to be given up, and that whatever replaced it would be something we did not yet have the concepts for. He closed the paper with a joke, which I find almost unbearable in retrospect. He referenced a line from a grim fairy tale about being owed a coin, a tailor, as a way of saying that the full theory still owed him an answer. He never collected it. On the night of the 6th of August, 1937, at the height of the Great Purge, Matvei Bronstein was arrested. The story that has come down, and it comes from his family, is that when the officers demanded he hand over his weapons and his poisons, he laughed at them. He was executed by shooting in a Leningrad prison on the 18th of February, 1938. He was 31 years old. His wife spent the following 2 years trying to find out what had happened to him, and was told nothing, and continued to submit appeals on behalf of a man who had already been dead for 18 months, because the state did not consider that information she was entitled to. He was formally rehabilitated in 1957, which is the Soviet term for an official acknowledgement that the person you killed had not done anything, and his physics disappeared. This is the part I want to be precise about, because it would be easy to reach for the word suppressed, and it is not quite the right word. Nobody banned Bronstein's paper. There was no committee that decided his result was inconvenient. What happened is simpler, and if you think about it for a while, more corrosive. He was killed. His name became dangerous to cite. The paper was in Russian in a Soviet journal at the beginning of a world war, and the physicists who might have followed up on it either did not know it existed or knew better than to mention it. So the field re-derived his conclusion from scratch 20 and 30 and 40 years later, and for decades did not know whose conclusion it was. The measurability argument was rediscovered. The black hole limit was rediscovered. The conclusion that geometry would have to be abandoned was rediscovered repeatedly by people who had never heard his name. It was not until Gennady Gorlick and Viktor Frankl published a full scholarly biography in 1994, more than half a century after his death, that the recovery was properly done. And it is only in the last 20 years or so that you will reliably find Bronstein cited in review articles as the origin point of the subject. Stanley Deser, one of the founding figures of modern quantum gravity, wrote an introduction to the English translation of that 1936 paper in which he acknowledged, essentially, that Bronstein had got there first and that the field had spent decades unaware of it. Freeman Dyson wrote about him. A piece in Scientific American some years ago asked, pointedly, why the people working on quantum gravity do not pay their tailor to the memory of Matvei Bronstein. Here is what I think that pattern is actually made of, and it is not a conspiracy, and it is not the NKVD. Physics does not have a memory, it has a citation graph. If a result is not in the chain of papers that people are currently reading, it does not exist for practical purposes, no matter how correct it is. And a citation graph is not a neutral record of what was discovered. It is a record of who was in the room, who was writing in a language that the people with grant money read, and who was alive long enough to keep pushing. That is the same mechanism that erased George Johnston Stoney, running at a far higher temperature. Which brings us to the uncomfortable part of Bronstein's argument, the part that I have been holding back. Because there is an objection to everything I have just told you. And it is a good objection, and if you have any background in this, you may already have made it. Everything Bronstein did was a measurement argument. It says that you cannot measure the gravitational field below a certain precision, and that any attempt to do so collapses into a black hole. But there is a difference between saying you cannot measure something and saying the something is not there. The universe is not obliged to stop existing at the edge of our instruments. Plenty of physics deals with things that cannot be directly observed, so Bronstein alone does not close the case. What he gives you is a warning that the theory is going to break. It is suggestive, it is elegant, and it is not a proof. The proof took another 50 years, and it did not come from thinking about measurement at all. It came from a calculation so long and so miserable that it required a computer to finish, and when it finished, it produced a single number that ended the entire program of treating gravity like every other force in nature. To understand what that calculation proved, you need one idea. And it is the single most important idea in 20th century theoretical physics, and it is almost never explained honestly to a general audience because the honest version is slightly humiliating. When you do a quantum field theory calculation, you are adding up every way a process could happen. An electron scatters off another electron, and you add up the simple exchange of a photon, and then the exchange with a small correction, and then the correction to the correction, and so on. Each layer is called a loop, and each loop involves integrating over all possible energies for the particles inside it, including infinite energy. And when you do those integrals, they come out infinite. Not large. Infinite, the theory, taken at face value, predicts that the mass of the electron is infinite, and the charge of the electron is infinite, which is a problem, because we have measured both. The fix, worked out in the late 1940s by Feynman, Schwinger, Tominaga and Dyson, is called renormalization, and what it amounts to is this. You accept that the parameters written in your equations are not the ones you measure. You take the infinity produced by the calculation and you absorb it into a redefinition of the parameter, and you fix the parameter by going into a laboratory and measuring the actual value once. After that, every other prediction the theory makes comes out finite and correct. Feynman himself called it a dippy process and said he suspected it was not mathematically legitimate. Dirac hated it until the day he died. It works to an absurd degree. The magnetic moment of the electron, computed this way, agrees with experiment to about 12 decimal places, which remains the most precise agreement between theory and measurement in the history of science. But it comes with a condition, and the condition is everything. Renormalization only works if the number of infinities you have to absorb is finite. If a theory produces 3 kinds of infinity, you measure 3 numbers in a laboratory and you are done forever. That theory is renormalizable and it has predictive power, because after those 3 measurements, it makes infinitely many predictions for free. If a theory produces a new kind of infinity at every loop order, then every loop requires a new measurement to fix it. You would need infinitely many experiments before the theory could tell you anything you did not already put in. That theory is non-renormalizable. It is not wrong. Exactly. It is empty. It has the form of a prediction machine with no fuel. For decades, nobody knew which category gravity fell into. In 1974, Gerard Hooft and Martinus Veltman, who would later share a Nobel Prize for renormalizing the electroweak theory, worked out the first loop for gravity. Their result was published in the Annales of the Henri Poincaré Institute, and it was ambiguous in the most tantalizing possible way. Pure gravity, gravity by itself in an empty universe, came out finite at one loop. The infinities cancelled. But the moment you added any matter at all, so much as a single scalar field, the cancellation failed and the divergences appeared immediately. So gravity in a universe with nothing in it was fine. Gravity in a universe with anything in it was not. And that left the crucial question open, because the cancellation at one loop might have been a coincidence of that particular order, or it might have been a sign of some deep hidden symmetry that would protect the theory all the way up. Finding out required going to two loops, and two-loop quantum gravity is one of the hardest calculations anyone has ever attempted. The Einstein equations are non-linear, which means the graviton interacts with itself, which means the number of terms explodes. Estimates run to tens of thousands of individual contributions, each of which has to be handled correctly, with no errors, because a single sign mistake anywhere invalidates the entire result. It took over a decade. It was finished by Mark Goroff and Augusto Sagnotti, using some of the first serious computer algebra ever deployed on a physics problem, and published in 1985 in Physics Letters B under the title Quantum Gravity at Two Loops, with the full version following in Nuclear Physics B in 1986. The answer was a single non-zero number. The divergence does not cancel at two loops. It survives, attached to a term built from 3 powers of the Riemann curvature tensor, and the coefficient in front of it is 209, divided by 2,880 times 4 pi to the 4th power. That fraction is the death certificate of an entire research program. Carlo Rovelli, writing the history later, described it as nailing the corpse of perturbative general relativity as a quantum field theory into its coffin. Independent confirmation came from Anton von der Ven in 1992 using different methods, and it holds. Einstein's theory of gravity is non-renormalizable, not suspected to be, not probably, but calculated, published, and independently confirmed. If you try to treat space-time curvature as a quantum field the way you treat the electromagnetic field, you get a theory that requires an infinite number of measurements before it can make a single prediction, and there is no clever trick, because the trick was tried by the best people available for a decade, and the answer was 209 over 2,880 times 4 pi to the 4th. And now, I have to do something that I think is the difference between this and a bad version of this, which is to immediately undercut the drama I have just spent 10 minutes building. Because the sentence physics cannot describe gravity as false. It circulates constantly, and it is not what that result means. In 1994, John Donoghue published a paper in Physical Review D, pointing out something that had been sitting in plain view. Non-renormalizable does not mean useless. It means the theory has a domain of validity and a scale at which it stops working, which is a completely ordinary situation. Fermi's theory of beta decay was non-renormalizable too. It was also correct for decades at the energies people could reach, and its breakdown scale was the clue that led to the discovery of the W boson. Treated the same way as what is called an effective field theory, quantum gravity works fine. It makes finite, unambiguous, parameter-free predictions at low energy. Donoghue computed one. There is a quantum correction to Newton's law of gravitation, a genuine quantum gravity effect, and its size is set by a coefficient of 41 over 10 pi, multiplying a term that falls off as the inverse square of the distance times Planck's constant over the speed of light cubed. That number, 41 over 10 pi, is a real prediction of quantum gravity. It is not speculative. It is not interpretation dependent. It is what you get. It is also so small that measuring it is hopeless by a margin that makes the Large Hadron Collider look like a promising instrument. But it exists, and it is derived. And anyone telling you that quantum gravity has never predicted anything is overstating the case. So the honest formulation, the one you will find in the technical literature and essentially nowhere else, is this. Physics does not stop working at the Planck scale. Physics stops being able to tell you anything you did not already know. At low energies, the infinitely many correction terms are suppressed and you can ignore all but a few. As you approach the Planck energy, they all become the same size at once. Every one of the infinitely many terms matters equally, each carries an unknown coefficient, and there is no experiment that could ever fix them. The theory does not break down in the sense of giving wrong answers. It dissolves into a structure with infinitely many free parameters, which is the mathematical form of having nothing to say. That distinction matters, and I have almost never seen it drawn in public. A theory that gives you wrong answers is a theory you can catch out. A theory that gives you no answers is a theory that cannot be caught out. And there is a very large amount of quantum gravity research that has been living comfortably in that gap for 40 years. Which brings me to the misconception I most want to correct in this entire piece, and it is one that I would guess 100 million people currently believe. The Planck length is not the pixel size of the universe. You have heard it described that way. Reality has a resolution. Space is made of tiny, discrete chunks. The universe has a smallest possible distance the way a screen has a smallest possible dot. It is repeated in documentaries, in popular books, in a very large number of videos, and it is presented as established fact. It is not established. It is not a fact. Nobody has ever observed it. It is one family of guesses among several, and the competing family, which I will come to, says the opposite and is taken just as seriously by professionals. What the Planck length actually marks is the scale at which our theories lose predictive power. That is a statement about our theories. Whether the world does anything special there is a separate question, and it is open. Sabine Hossenfelder, who wrote the definitive technical review of this in Living Reviews in Relativity in 2013, frames the entire subject as a survey of model-dependent scenarios, not as a description of reality. Every serious paper on this uses the phrase minimal-length scenarios. Scenarios, the plural, is doing a lot of work. There is a whole literature building models where a minimum length exists. The generalized uncertainty principle, which modifies Heisenberg's relation so that position uncertainty has a flaw, was developed in a sequence of papers starting with Amati, Schiaffelloni and Veneziano in 1989, then Konishi, Perfuti and Prevero in 1990, then Maggiore in 1993, then Scardigli in 1999. It is elegant and I find it persuasive on aesthetic grounds. But 3 of those 4 derivations come out of string theory and inherit its assumptions. Only Scardigli's, which uses nothing but the uncertainty principle and the formula for the radius of a black hole, is genuinely independent of any specific model of quantum gravity. That is one model-independent argument, resting on a thought experiment for the most confidently repeated claim in popular physics. And here is what I think is really going on, which is the thing I want you to carry into the next hour. Look again at what actually fails in the Goroff and Sagnotti calculation. The infinities do not appear because space-time is too small to describe. They appear because the description assumes a smooth background manifold that you can integrate over, and then discovers that the integration eats itself. The failure is not located in the world, it is located in the noun. We have been treating space as a thing that has parts, and a theory that treats space as a thing with parts breaks in exactly the way you would expect a theory to break if space were not a thing with parts. Nobody in 1986 said that out loud. It took another decade before anyone had the tools to say it seriously, and when they did, it did not come from quantum gravity at all. It came from thermodynamics. But before we get there, I need to show you why the simple fix, the obvious fix, the one everybody reaches for the moment they hear about a minimum length, does not work. Because if you make space discrete, you break relativity, and not in a subtle way that shows up at the 18th decimal place. You break it so badly that it is visible in the geometry of a right-angled triangle. In 1949, Hermann Weyl published a book called Philosophy of Mathematics and Natural Science, and on page 43, he put an argument into print that takes about 4 sentences and has never been satisfactorily answered. Suppose space is made of tiles. Little discrete squares, whatever size you like, and distance means counting how many tiles you cross. Now draw a square that is 100 tiles along each side and draw its diagonal. How many tiles does the diagonal cross? 100, because to get from one corner to the other, you move one tile across and one tile up, 100 times, and each of those diagonal steps is one tile. So the diagonal of the square is the same length as the side, but Pythagoras says the diagonal should be the side times the square root of 2, which is about 1.414. The tiled answer is off by about 29%. And here is the part that makes it lethal. The error does not go away when you make the tiles smaller. Make them 1,000,000 times smaller and you get 1,000,000 steps instead of 100. And the ratio is still exactly 1 instead of 1.414. The discrepancy is scale invariant. It survives all the way down and all the way up. If space were made of tiles, in the naive sense, the geometry of a triangle would be visibly wrong at every scale including this one, and it is not, because you can go and measure a triangle. That is Weyl's tile argument, and it has been sitting in the philosophy of physics literature for 77 years. John Paul van Bendeghem attempted a rebuttal in 1987. The most recent serious treatment I know of is a paper by Lu Chen in the British Journal for the Philosophy of Science, published in 2025, arguing that the argument fails for reasons that are technical and, to be honest with you, that I do not find completely convincing. Causal set theory has the best escape route, and I will come to it, because it is genuinely clever and it involves throwing the points down at random rather than laying them out in a grid. But the general lesson holds. You cannot fix quantum gravity by pixelating space. Pixelating space is not a simplification. It is a new and worse problem, and it gets worse than a triangle, because the real objection is not geometric, it is relativity. A minimum length is a length, and in special relativity, lengths are not invariant. A meter stick moving past you at high speed is measured as shorter than a meter. That is not an optical illusion or a measurement artifact, it is the actual result, confirmed in particle accelerators every day of the week. So suppose there is a fundamental minimum length, 1.616 times 10 to the negative 35th of a meter, and suppose I am at rest with respect to it. Now you fly past me at 99% of the speed of light. You measure that same fundamental minimum length as shorter than the minimum length, which is a contradiction in terms. There are only two ways out of that, and both of them cost you something you did not want to spend. The first is that you break Lorentz symmetry. You accept that there is a preferred frame in the universe, some particular state of motion in which the laws take their simplest form and the minimum length is what it is, and everybody else is measuring a distorted version. That is a return to something very like the ether, and it has the enormous disadvantage that Lorentz symmetry is the single most precisely tested principle in all of physics. The second is that you deform relativity itself, so that the transformation rules are modified in a way that leaves both the speed of light and the Planck length invariant. This is called doubly special relativity, and it was developed by Giovanni Amelino Camiglia in a pair of papers in 2001 and 2002, and independently by Jumagwejo and Lee Smolin in Physical Review Letters in 2002. It is a real and serious mathematical structure. It also has a problem that its own community named, with commendable honesty, the soccer ball problem. If you modify the rules for how momenta add together so that no momentum can exceed the Planck momentum, then those modified rules apply to everything, including composite objects. A football contains something like 10 to the 25th atoms. Add up all their momenta using the deformed rules and you get nonsense. The theory says a kicked football cannot exceed a momentum threshold that a kicked football exceeds routinely. The objection is generally credited to Iwo Bialaniki Birula in the early 1990s. The name was coined informally within the community itself, and the most careful analysis of it is Hossenfelder's paper in the journal Sigma in 2014. There are proposed solutions, one of which is a framework called relative locality, in which whether two events happen at the same place depends on who is looking, nobody I have read considers the matter settled. So here is where we actually are, and I want to state it plainly because the accumulation matters. Space cannot be smooth all the way down, because the theory that describes smooth space produces infinities that cannot be absorbed. Space cannot be a lattice, because a lattice gets the diagonal of a square wrong by 29% at every scale. Space cannot have a minimum length in the ordinary sense, because a minimum length is not compatible with the most precisely verified symmetry in physics. Every option on the obvious list is excluded. That is not a gap in knowledge. That is a set of walls. Which means, at this point, it is somebody's job to go and look. And people have, and I want to walk through what they found, because this is the section that almost never gets made, and it is the section that changed my own view of this subject more than anything else. The first serious idea was that if spacetime is grainy, light should trip over it. A photon travelling through a discrete or foamy spacetime might have its speed depend very slightly on its energy, the way light in glass does. The effect for any single photon would be immeasurably small, but if you let it accumulate over billions of light years, it becomes detectable. High-energy photons from a distant explosion would arrive at a measurably different time from low-energy ones emitted at the same instant. Gamma-ray bursts are the ideal source. On the 10th of May, 2009, the Fermi Large Area Telescope observed a short gamma-ray burst designated GERB 090510 at a redshift of 0.903, which puts it around 7.3 billion light-years away. Among the photons it detected was one with an energy of 31 billion electron volts, which is the highest energy photon ever seen from a short burst at that point. That photon had been travelling for over 7 billion years alongside photons of a millionth of its energy. If spacetime had any graininess at the linear order that most models predicted, they would have separated. They arrived together. The result was published in Nature, and the constraint was brutal. It ruled out linear energy-dependent photon dispersion at the Planck scale, and then it kept going, excluding the effect up to 1.2 times the Planck energy. A more careful analysis published in Physical Review D in 2013 pushed the bound to 7.6 times the Planck energy. Read that again, because it is easy to skim past. The experiment did not fail to reach the Planck scale. It went past it and found nothing there. An entire class of quantum gravity models that had been written about for a decade, were eliminated by a single photon from a dying star. Then it happened again, from a completely different direction. On the 17th of August, 2017, LIGO and Virgo detected gravitational waves from two neutron stars colliding, and 1.74 seconds later, the Fermi Gamma-ray Burst Monitor detected the light. The signals had been travelling together for about 130 million years. A delay of 1.74 seconds after 130 million years of flight constrains the difference between the speed of gravity and the speed of light to somewhere between -3 parts in 1,000 trillion and +7 parts in 10,000 trillion. That measurement killed an entire literature. Whole families of modified gravity theories, some of them decades old, some of which had been proposed as alternatives to dark energy, were eliminated in an afternoon. There are physicists who lost their research programs on the 17th of August, 2017, and did not find out for 2 months. Then, neutrinos. IceCube, which is a cubic kilometre of instrumented Antarctic ice at the South Pole, has used astrophysical neutrinos to constrain deviations from Lorentz invariance to below 1 part in a billion billion, improving on the previous best limit by 5 orders of magnitude. Their most precise search, published in Nature Physics in 2022, found what the collaboration described as no sign of anomalous behaviour. Cosmic ray observations from the Pierre Auger Observatory in Argentina push comparable bounds in the hadronic sector, in several cases beyond the Planck scale as well. And then there is the Holometer, which is the one I think about most. Craig Hogan, a cosmologist at the University of Chicago and Fermilab, proposed that if the holographic principle is right and the information content of a volume of space really is limited by its surface area rather than its volume, then spacetime should have a specific and detectable kind of quantum jitter. Not random noise, but correlated transverse fluctuations, a sort of shared uncertainty in position that would show up as a characteristic hum in a sufficiently sensitive interferometer. He got it built. 2 40-meter laser interferometers at Fermilab, nested and overlapping, so that genuine spacetime jitter would show up as a correlation between them, while ordinary local noise would not. It ran for years. The sensitivity achieved was extraordinary, well beyond what the original proposal required. The result, published in 2015, was nothing. Not a hint. Fermilab's own announcement was headlined that the Holometer had ruled out the first theory of spacetime correlations, which is an unusually blunt way for a laboratory to describe its own flagship experiment. Hogan's response was that this was the beginning of the story rather than the end, that they had developed a new way of studying space and time that had not existed before, and that they had not been certain they could reach the sensitivity they reached. Which is true, and which is also, if you read it in a certain light, the sound of a man watching a decade of work come back empty. Sabine Hossenfelder's assessment was less generous. Her position, stated publicly at the time, was that the underlying model had never been consistent with other known physics, that the null result was therefore unsurprising, and that the experiment taught us nothing and wasted time and money. I do not know which of them is right. I lean, if I am honest, somewhat toward Hogan, because the alternative is a physics that never tests anything it cannot guarantee in advance, and that is not a physics. But look at the pattern, because the pattern is the point. 4 independent classes of experiment: gamma-ray timing, gravitational wave timing, neutrino propagation, and direct interferometry. Every one designed to detect Planck scale structure. Every one sensitive enough to have seen the effects that had been predicted. Every one came back empty, and in 2 cases the constraint went past the Planck scale and kept going. And the response of the field, collectively, was to observe that those had never been the good models anyway. I want to be careful here, because that response is not dishonest. It is often correct. Ruling out linear dispersion genuinely does not rule out quadratic dispersion, and the surviving models genuinely do predict smaller effects. That is how science is supposed to work. You constrain, you refine, you go again. But there is a version of that move which cannot be distinguished from the honest version from the outside, and it is the version where every failed prediction retreats to a slightly smaller effect, indefinitely, and the theory can never be wrong, because there is always another decimal place to hide behind. 40 years in, with 0 confirmed predictions from any program, I do not think it is unreasonable to ask which version we are watching. And then there is the possibility that nobody wants to say into a microphone, which is that the experiments came back empty because there is nothing down there to find. Not nothing in the sense of empty space, nothing in the sense that the question was malformed, because there is one more option on the list, and it is the one where the wall is not a wall at all. In 1979, Steven Weinberg contributed a chapter to a centenary volume on general relativity, in which he made a suggestion that was largely ignored for 20 years and is now one of the most active programs in the field. Weinberg pointed out that the argument I gave you earlier, the one about non-renormalizability and infinitely many parameters, contains a hidden assumption. It assumes that you calculate by starting from the free theory and adding corrections one at a time. That is called perturbation theory, and it is how essentially all of quantum field theory is done. And it is not the only way. If instead, the coupling constants of gravity run with energy and approach a fixed point at high energy rather than running off to infinity, then the theory could be perfectly well defined all the way up, with only a finite number of free parameters, even though it looks hopeless order by order. Weinberg called this asymptotic safety, For 2 decades, nobody could check. Then in 1998, Martin Reuter published a paper in Physical Review D applying a technique called the functional renormalization group to gravity, and found evidence for exactly such a fixed point. The evidence has held up under successive refinements, and the program now has hundreds of practitioners. Here is what asymptotic safety means, if it is right. There is no minimum length. There is no graininess. There are no atoms of space, no pixels, no discrete network of causal events. Spacetime is a smooth continuum all the way down, forever, with no bottom. And the Planck length is not a flaw, but simply the scale at which the coupling constants stop changing, and the theory becomes scale invariant. Reuter and Jan Markus Schwint looked at this directly in 2006 and concluded that in asymptotically safe gravity, there is no minimal proper length. What there is instead is a minimal angular resolution, which is a genuinely strange thing to find and which I do not have a good intuition for. But it is not the same as space being made of bits. So the entire pixel picture, the thing that everyone believes, has a serious, well-funded, mathematically sophisticated rival that says the exact opposite, and if you asked a room of quantum gravity researchers to vote, you would not get a consensus. You would get an argument. Now let me give you the other camp properly, because the discrete side is not a fringe position, and some of it is beautiful. Start with John Archibald Weyl, who is a complete character in his own right. Weyl studied under Bohr in Copenhagen in the 1930s, was Feynman's doctoral supervisor, worked on the Manhattan Project, and then on the hydrogen bomb, and had a gift for naming things that has shaped how everybody talks about physics. He coined black hole, he coined wormhole, and in 1955, in a paper in Physical Review titled simply Geons, he introduced the idea that at very small scales the quantum fluctuations of the geometry of spacetime itself would become so violent that the smooth manifold would dissolve into a churning, topologically chaotic mess. He called it spacetime foam. Wheeler's own image for it was the ocean. From an aeroplane at 30,000 feet, the sea looks like a smooth blue plane. Come down to 100 meters and you see waves. Get into a lifeboat and you see foam forming and breaking, structures appearing and vanishing, no smooth surface anywhere. His claim was that spacetime is like that, and that the Planck length is the altitude at which you finally see the foam. Late in his life, Weyl went somewhere stranger. He became convinced that information, not geometry, was the fundamental thing, and he compressed the idea into a phrase, it from bit, arguing that every physical entity derives its existence from binary answers to yes-no questions. He talked about law without law, the idea that the regularities we call physical laws might not be fundamental at all but statistical residue. Some of his colleagues thought he had drifted into mysticism in his final decades. Hold on to it from bit, because it is going to turn out to be the least mystical thing in this entire story. Then there is loop quantum gravity, which is the most technically developed version of the discrete picture. It starts with a reformulation of general relativity that Abhay Ashtekar published in Physical Review Letters in 1986, which recast Einstein's theory in variables that look much more like the variables of the other forces, and made quantization tractable for the first time. The central result came in 1995, when Carlo Rovelli and Lee Smolin published a paper in Nuclear Physics B titled Discreteness of Area and Volume in Quantum Gravity. What they showed is that in this formulation, area and volume are not continuous quantities. They are operators with discrete spectra, like the energy levels of an atom. Area comes in specific allowed values and nothing in between. The smallest possible non-zero patch of area is 4 pi times the square root of 3, multiplied by a parameter called the Emergent parameter, multiplied by the Planck area. That is a striking claim. It says a surface cannot have just any area. It says there is a smallest patch, and that asking about anything smaller is like asking about an energy level between the first and second in a hydrogen atom. But there is a problem sitting in the middle of that formula, and it is that emergency parameter. It is a free number. The theory does not predict it, and the way its value gets fixed is by calculating the entropy of a black hole in loop quantum gravity, comparing the answer to the Bekenstein and Hawking formula that we already knew from other arguments, and then choosing the value of emergency that makes them match, which turns out to be about 0.2375. Critics have called that circular, and I think the criticism has teeth. The fundamental quantum of area, the thing the whole discrete picture rests on, is calibrated against a result the theory was supposed to explain independently. It is not fatal, and Ravelli and Thomas Tiemann have written at length defending the procedure, but it is not the clean derivation the popular accounts imply. Then, causal set theory, which I have a soft spot for because it is the most radical of the lot, and the most honest about it. In August of 1987, Luca Bombelli, Johann Lee, David Meyer and Raphael Sorkin published a paper in Physical Review Letters with the title Spacetime as a Causal Set. Their proposal is that the fundamental structure of the world is not a geometry at all. It is a set of discrete elements with a partial order on them, which is to say a list of which events can influence which other events, and nothing else. No distances, no coordinates, no metric. Sorkin's slogan for it is that order plus number equals geometry. The causal relations give you the shape, and counting the elements gives you the volume, and everything else. Including the smooth spacetime we live in is a large-scale approximation of that, and crucially, causal sets escape Weyl's tile argument. Because the elements are not laid out in a lattice, they are scattered at random through spacetime by a process called Poisson sprinkling, and a random scatter does not have preferred directions, which means it does not get the diagonal wrong. It is a genuine solution to a 77-year-old objection, and it took discarding the idea of a grid entirely to find it. Causal set theory also has the only thing in this entire field that looks like a successful prediction, and I have to handle this one carefully because it is routinely oversold, and it is also genuinely impressive. In the late 1980s and early 90s, Sorkin argued that if spacetime is a causal set, then the cosmological constant should not be zero. It should fluctuate, with a magnitude set by the number of elements in the observable universe, which works out to a value around 10 to the minus 120 in Planck units. He was arguing this before 1998, which is when the supernova observations of Reese, Perlmutter and Schmidt showed that the expansion of the universe is accelerating and that the cosmological constant is not zero and is about 10 to the minus 120 in Planck units. That is remarkable, and it deserves more attention than it gets. It is also, and I want to be straight with you, an order of magnitude argument resting on a fluctuation ansatz, not a sharp numerical prediction, and the underlying dynamics needed to make it rigorous still do not exist. It is the best thing on the board, and it is not proof. And then there is causal dynamical triangulations, which produced, in 2005, the single strangest result in this whole subject. Jan Ambjorn, Jerzy Jurkiewicz and Renat Loll build spacetime out of small simplices, 4-dimensional triangles, glued together in every possible way consistent with causality, and then sum over all the configurations numerically. It is a computer experiment. You are simulating quantum spacetime and measuring its properties. In October of 2005, they published a paper in Physical Review Letters called Spectral Dimension of the Universe. The spectral dimension is what you get if you release a random walker into a space and watch how quickly it spreads out. In ordinary 4-dimensional space, it spreads at a specific rate. On a fractal or a foam, it spreads differently. At large scales, their simulated spacetime had a spectral dimension of 4.02 plus or minus 0.1. 4 dimensions, exactly as expected, emerging from a structure that had not been told to be 4-dimensional. At very small scales, the dimension dropped toward 2. Their reported value at short distance is around 1.8, with an uncertainty of about 0.25. Their spacetime was 4-dimensional when you looked at it from far away, and approximately 2-dimensional when you looked at it up close. That is already odd. But this is the part that makes it worth an hour of anyone's attention. The same result appears in asymptotic safety. Oliver Lauscher and Martin Reuter found the same flow from 4 dimensions to 2, published in the same year, from a completely different method with completely different assumptions. It appears in Horava Gravity. Petter Horava published a paper in Physical Review Letters in 2009 constructing a theory in which the dimension flows from 4 to 2 by design, and then found that his construction reproduced the numerical results. It appears in Loop Quantum Gravity, in the spin foam formulation. 4 independent approaches built by different people on different foundations, using different mathematics that agree about almost nothing, all report that spacetime becomes approximately 2-dimensional at short distances. Stephen Carlip, who wrote the review article on this in Classical and Quantum Gravity in 2017, treats it as one of the few pieces of genuine evidence about the Planck scale that we have, and also, being a careful person, notes that the spectral dimension is a probe-dependent quantity, and that the agreement might be an artifact of how the question is posed rather than a fact about the world. I do not know which it is, nobody does, but 4 approaches converging on a number they were not designed to produce is the kind of thing that in any other area of physics would be taken very seriously indeed. Now, string theory has its own version of all of this, through a property called T-duality, which says that a string theory compactified on a circle of a given radius is physically identical to one compactified on a circle of the inverse radius. If you try to shrink a dimension below the string length, you do not get a smaller universe. You get the same physics you would have got by making it bigger. Geometry folds back on itself. There is a minimum meaningful size, and the reason has nothing to do with the smallest brick. The reason is that below that size the question stops distinguishing between 2 answers, and the caveat that gets dropped constantly is that the string scale is not necessarily the Planck scale. It depends on the string coupling and on how the extra dimensions are wrapped up, and it can be considerably larger. So there it is, 6 answers. Asymptotic safety says space is continuous with no minimum length. Loop quantum gravity says area and volume are quantist with a smallest patch. Causal sets say there is no geometry at all, only a discrete order of events. Causal dynamical triangulations says spacetime loses 2 of its dimensions on the way down. String theory says geometry becomes ambiguous below a scale. Wheeler's foam says the topology itself boils. They disagree about whether space is discrete. They disagree about whether there is a minimum length. They disagree about how many dimensions there are down there. They disagree about whether geometry exists at all. Not one of them has a confirmed experimental prediction. Several of them are mutually exclusive. And every single one of them agrees on one thing. Not one of them defends the smooth, continuous, infinitely divisible spacetime you were taught in school. Not one. Even asymptotic safety, the most conservative program in the field, the one that keeps the continuum, has to make the number of dimensions depend on the scale at which you look. The manifold survives in name and loses the property that made it a manifold. That is the consensus. That is the thing that unites 6 theories which agree on nothing else. The thing everybody believes, the thing you were taught. The thing that underlies every equation you have ever seen written down is the one thing that no serious contemporary approach to quantum gravity is willing to defend. And nobody says it in public in those terms, because saying it in those terms requires admitting that we do not have a replacement. But there is a 7th answer. It is not on that list, because it is not a theory of quantum gravity at all. It came out of thermodynamics in 1995, and if it is right, then everybody on that list has been asking the wrong question for 40 years. Ted Jacobson was working at the University of Maryland when he published a 4-page paper in Physical Review Letters in 1995 with the title Thermodynamics of Spacetime, and the subtitle, which is the part that matters, calls the Einstein equation an equation of state. To explain what he did, I need to remind you what an equation of state is, and this is where the word I asked you to hold on to comes back. The ideal gas law says that pressure times volume equals the number of molecules times temperature times a constant. It is one of the most reliable relationships in physics, and it was discovered entirely by experiment, by people who had no idea molecules existed. Boyle, Charles and Gay Lussac worked it out from measurements on air in the 17th and 18th centuries. It works. But there is something about temperature and pressure that you have to hold on to. They are not properties of molecules. A single molecule does not have a temperature. It is not that we lack an instrument sensitive enough to measure the temperature of one nitrogen molecule. The concept does not apply. Temperature is a statistical description of the average kinetic energy of an enormous number of particles, and it comes into existence only when there are enough of them for the average to mean something. Pressure is the same. Ask how much pressure a single molecule exerts, and the question is malformed. So the ideal gas law is a true, precise, quantitatively accurate physical law about quantities that do not exist at the fundamental level. It is an equation of state. It describes emergent, collective statistical properties, and it tells you nothing whatsoever about atoms. You could have known the ideal gas law perfectly for 200 years and never suspected that matter was made of anything. Jacobson asked what would happen if you assumed that spacetime works the same way. He took a small patch of spacetime and constructed what is called a local Rindler horizon, which is the horizon that an accelerating observer sees. He assigned that horizon an entropy proportional to its area, which is the Bekenstein and Hawking result for black holes. He assigned it a temperature, which is the UNR result for accelerating observers. And then he applied the most basic relation in all of thermodynamics, the one that says heat equals temperature times change in entropy, and demanded that it hold for every such patch, everywhere, for every observer. Out came the Einstein field equations. All of them, the full non-linear equations of general relativity derived from thermodynamics, in 4 pages. Take a moment with that, because I think it is the most under-discussed result in modern theoretical physics, and I have never seen it explained properly outside a seminar room. Jacobson did not find a thermodynamic analogy for gravity. He derived the exact equations of general relativity, the ones that predict the bending of starlight and the precession of Mercury, and the existence of black holes and the frequency of gravitational waves, from the assumption that space-time has an entropy and obeys the first law of thermodynamics. And in his own paper, he draws the conclusion, which is that this suggests the Einstein equation is an equation of state, which means that trying to quantize it, trying to find the quantum theory of the gravitational field the way we found the quantum theory of the electromagnetic field, would be a category error of a very specific and embarrassing kind. It would be like trying to build a quantum theory of pressure, like looking for the pressure particle. You can do the mathematics and you will get something, and it will be non-renormalizable, because there is no fundamental field there to quantize. Pressure is not made of anything. It is what a lot of something else does. Every failure I have described to you in the last hour and a half is exactly what you would expect to see if that were true. The infinities in Goroff and Sagnotti, the measurability limit Bronstein found, the impossibility of a minimum length that respects relativity, the 40 years of experiments coming back empty. Every one of them is the signature of a field asking for the microscopic theory of a quantity that is not microscopic. Now I want to be as honest about the limits of this as I have tried to be about everything else. Jacobson's derivation has been analysed and criticised heavily for 30 years. There are questions about whether the entropy assignment is justified, whether the argument is fully general, and whether it establishes emergence or merely demonstrates a consistency relation. Eric Valindi published a much more aggressive version in 2011, arguing that gravity is literally an entropic force, and it took serious damage, partly from neutron interferometry experiments showing quantist gravitational bound states which are difficult to reconcile with the picture. Jacobson's original result is far more robust than Verlinde's extension, and it is still not universally accepted as proof of emergence. But it does not stand alone, and the other pillars are what make it hard to dismiss. The first is the holographic principle. In 1993, Gerard de Hooft, and in 1995, Leonard Susskind, in a paper titled The World as a Hologram, argued that the maximum amount of information that can be contained in a region of space scales, not with the volume of the region, but with the area of its boundary. Suskind's formulation is that the description requires one discrete degree of freedom per Planck area. The number comes from black hole thermodynamics. The entropy of a black hole is its horizon area divided by 4 Planck areas. Convert that to bits, and you get roughly 1 bit for every 4 Planck areas of surface. Raphael Bousso generalized it in 1999 into what is called the covariant entropy bound, which applies to any surface in any spacetime, and it has survived every attempt to violate it. Think about what that means for a room you are sitting in. The maximum information content of that room is not set by its volume, it is set by its walls. If you keep adding information to the room, you do not run out of space in the middle, you run out of surface, and at the moment you exceed the bound the room collapses into a black hole. That is not how a three-dimensional thing behaves, that is how a projection behaves. And the second pillar is the one that I think will eventually be regarded as the turning point, and it came from a short essay written for a prize competition. In 2010, Mark van Ramsdonk wrote a piece called Building Up Spacetime with Quantum Entanglement. He was working within the correspondence discovered by Juan Maldacena in 1997, which relates a theory of gravity in a volume of space to a quantum theory without gravity living on the boundary of that space. Van Ramsdonk asked a simple question. If the boundary theory encodes the geometry inside, then what feature of the boundary theory corresponds to distance? The answer was entanglement. He showed that if you take the quantum state on the boundary and gradually reduce the entanglement between 2 regions of it, the geometry inside responds. The 2 corresponding regions of space move apart. Reduce the entanglement to 0, and the space does not just become large, it disconnects. The 2 regions cease to be part of the same spacetime at all. There is no distance between them, not because they are far apart, but because distance has stopped being defined between them. Distance, in that framework, is a measure of entanglement. Maldacena and Susskind pushed it further in 2013 with a conjecture usually written as ER equals EPRA, proposing that the Einstein-Rosen bridge, a wormhole, and Einstein-Podolsky-Rosen entanglement are the same thing described in 2 different languages. 2 entangled particles are connected by a wormhole, not analogous to, connected by. The caveat, and it is a large one that I am not going to soften, is that all of this is established in a universe that is not ours. The Maldacena correspondence works in anti-de Sitter space, which has negative curvature and a boundary at infinity where the dual theory can live. Our universe has positive curvature, is accelerating, and has no such boundary. Nobody has been able to construct a version of this for the actual world we are in, and there are structural reasons to think it may be hard. Every statement in the last few minutes is a statement about a very well understood toy model. But the toy model is the only place we have ever been able to do the calculation at all, and in the only place we can check, the answer is that geometry is made of entanglement. Which brings me to what senior people say when they are talking to each other rather than to a camera. Nima Arkhani Hamed is one of the most influential theoretical physicists alive. In the Messenger lectures at Cornell in 2016 he said, and this is his phrasing, that space-time is doomed, that there is no such thing as space-time fundamentally in the actual underlying description of the laws of physics. He has said elsewhere that almost everyone in the field believes this, and that the problem is that nobody knows what replaces it. He has given lectures with titles that state it flatly. The Doom of Spacetime, at a scientific society in Washington in December of 2017. The End of Spacetime, at Stanford in June of 2018. The abstracts say that the union of quantum mechanics and gravity strongly suggests spacetime is doomed, and that space and time will be seen to emerge from more primitive principles. That is not a fringe position, and it is not a provocation for a lecture title. That is a mainstream summary of where the field's leading figures actually are, and it is essentially absent from public science communication, where you will still be shown a rubber sheet with a bowling ball on it, and told that this is what gravity is. So the picture that assembles itself, and I want to stress that it is a picture rather than a result, is something like this. Space is not a container. Distance is not a property of the world. What exists at the fundamental level is some structure of quantum information, some pattern of entanglement or causal relation, or something we do not yet have a word for, and when you have enough of it, arranged in the right way, it behaves collectively in a manner that is very well described by saying that things have positions and are certain distances apart. Just as when you have enough molecules moving fast enough, the collection behaves in a manner very well described by saying it has a temperature. And the Planck length on this picture is not a smallest distance. It is the scale at which you no longer have enough of the underlying structure for the average to mean anything. It is not a wall. It is the point at which the statistic stops being computable, which is why nobody has ever detected the graininess. There is no graininess. There is nothing down there at all in the sense of a smaller thing. There is the absence of the conditions under which the word down means anything. I want to come back to Max Planck now. Because I said at the beginning that reading his 1899 sentence about extraterrestrial and non-human civilizations is difficult once you know what happened to him, and I have left that debt outstanding for 2 hours. Think about what he was reaching for in that paragraph. He was a deeply conservative man, temperamentally and politically, who had been told by his professor at Munich not to go into theoretical physics because everything important had already been discovered. He went in anyway, and he spent his career looking for the parts of nature that do not depend on us. That is what the whole Natural Units project is. It is an attempt to find a system of measurement that owes nothing to the length of a French king's arm, or the freezing point of water, or the rotation of this particular planet. Something that would still be true if there were nobody here. Something absolute. Then his life took every contingent human thing away from him, one at a time, over 36 years. His first wife, Marie, died in 1909 after 22 years of marriage. His eldest son, Carl, was killed at Verdun in 1916, in what was probably the worst place on the surface of the earth in that year. His daughter, Grete, died in childbirth in 1917. His other daughter, Emma, married Grete's widower and died in childbirth in 1919. Both of the children survived. They were named after their mothers. In 1933, after the Nazis took power and the dismissals of Jewish academics began, Planck went to see Hitler personally to argue for the scientists who were being removed. He was 75 years old, and he was the most senior figure in German science, and he thought that would count for something. The meeting went badly. Hitler flew into one of his rages, and Planck left having accomplished nothing. He then spent the following decade in an impossible position, staying in Germany, keeping the Kaiser Wilhelm Society functioning, being condemned by émigrés for collaborating, and by the regime for insufficient enthusiasm. In 1944, a bombing raid destroyed his house in Berlin, along with his library, his correspondence, and every scientific paper he had accumulated in 60 years of work. And in January of 1945, his last surviving son, Erwin, was executed. Erwin had been a senior civil servant and had been implicated in the July 20th plot to assassinate Hitler. He was condemned by the People's Court and hanged on the 23rd of January, 1945, with the war already lost and the Red Army 100 kilometers from Berlin. Planck had described Erwin as his best and closest friend. It has been suggested by some biographers that Hitler's memory of that 1933 meeting made him less willing to commute the sentence. Though I have not seen documentary evidence for that, and I am giving it to you as a claim rather than a fact. Planck wrote afterwards that if you think he has the strength to withstand this pain, you give him too much credit. He was 86. He lived another 2 years in a country that no longer existed and died in 1947. Now put that next to the sentence he wrote in 1899. Units that will retain their meaning for all times and for all civilizations, including extraterrestrial and non-human ones. He was looking for the one thing that could not be taken away. He found 4 numbers, and what those 4 numbers turned out to mark is the place where the last absolute thing in physics stops being absolute. Space itself, distance, the one property of the world that everybody, in every era, in every culture, has taken to be simply and obviously there. He located the edge of it, and he did not know that was what he was doing, and if he had known, I do not think it would have consoled him at all. There is one more debt, and then I am going to stop. Matvei Bronstein closed his 1936 paper with a joke about a fairy tale, about being owed a coin. The full theory owed him a tailor. He was making the ordinary sort of remark that a confident young theorist makes at the end of a paper. The sort of remark that assumes there will be a next paper, and a career and time. He had 18 months. And what he had already written down in that paper, at 29, in a language and a country and a decade that guaranteed nobody would read it, is the thing that 90 years of subsequent work has arrived back at. That the reconciliation would require the rejection of Riemannian geometry, and perhaps also the rejection of our ordinary concepts of space and time, replacing them with something much deeper and non-evident. Arkani Hamed's version, Spacetime is doomed, is the same sentence with the confidence of 80 additional years behind it. Delivered in a lecture hall at Cornell by a man who will not be shot for it. The tailor has not been paid, the concepts are still non-evident. The only thing that has been established in the intervening 9 decades is that Bronstein was right about the size of the problem, which is the least useful way to be right. So let me tell you what I think this actually means for you, sitting there, and then I will leave it alone. You have a sense, and it is so fundamental that it is difficult to even locate as an assumption, that things are a certain distance apart, that the screen is a certain distance from your face, that there is a definite, real physical gap between your hand and the surface it is resting on, and that if you had a fine enough ruler, you could keep dividing that gap. And keep dividing it, and there would always be a smaller piece. That intuition has no defenders left. Not one serious approach to quantum gravity says that the gap between your hand and the table is infinitely divisible in the way you imagine. The ones that keep the continuum have to change the number of dimensions as you descend into it. The ones that discretize it have to break the diagonal of a square or abandon geometry entirely. And the ones that have made the most progress in the last 20 years say that the gap is not a thing at all, that distance is a way of talking about how much 2 collections of quantum information know about each other, and that asking how far apart 2 points are, when there is not enough structure between them to support a statistic, is like asking for the temperature of a single molecule. Not a hard question, not an unanswered question, a question with no referent, phrased in a vocabulary that only works in bulk. And you are in bulk. That is what I keep coming back to. You are made of somewhere around 10 to the 28th atoms, in a body about 1 meter 8 tall, sitting in a room, on a planet, in a universe that has been running for 13.8 billion years, and every single one of those facts is a statement about an enormous aggregate. Every distance you have ever perceived, every gap you have ever crossed, every measurement anyone has ever made in the history of the species has been taken in a regime so far above the Planck scale that the underlying structure has been averaged into perfect smoothness. The way a photograph of the ocean from 30,000 feet is perfectly blue. The smoothness is real, in the sense that temperature is real. It is not an illusion, it is a description that works. It is just not a description of anything that is there. The last thing I want to leave you with is the timing, because I find it the hardest part to sit with. Bronstein worked this out in 1936, and nobody read it. Weyl proposed the foam in 1955, and it has never been observed. Goroff and Sagnotti closed the door in 1986. Jacobson derived Einstein's equations from thermodynamics in 1995, and it changed almost nothing about how the subject is taught. Van Ramsdonk showed that geometry falls apart when you remove entanglement in 2010. The Holometer looked for the graininess and found smoothness. The gamma-ray bursts looked and found smoothness. The neutrinos and the gravitational waves looked and found smoothness. 90 years, every result pointing the same direction, and the standard public presentation of what space is has not moved at all since 1915. You will still be shown the rubber sheet. You will still be told that mass curves space-time, as though space-time were a fabric with a texture, as though there were a substance there being bent, and the people telling you that know that there is not. And they tell you anyway, because the alternative requires saying that we do not know what the fabric is made of, or whether the word made is even the right word, or whether there is a fabric. That is not a lie, it is worse than a lie. It is a picture that was known to be inadequate before most of the people repeating it were born, kept in circulation because nothing has arrived to replace it, and because the honest version does not fit on a diagram. So here is the honest version. There is no smallest distance. There is no pixel. There is no fabric, and there is no foam, and there is no lattice. Or if there is, 90 years of the most sensitive experiments ever constructed have found no trace of any of it. What there is, at the bottom of every measurement any instrument has ever taken, is a scale at which the question stops meaning anything, and above which everything you have ever experienced takes place. The gap between your hand and the table is not a distance that we cannot measure precisely enough. It is a statistic that stops being defined before it reaches the bottom. And it does not reach the bottom. It stops 35 orders of magnitude short, and there is nothing underneath, and the nothing is not empty space. The nothing is the absence of the conditions under which space is a word. You will get up in a moment and cross a room. The room will hold. The distance will behave exactly as it always has, because there are enough atoms in the floor and enough structure in the vacuum and enough entanglement between here and there for the average to hold to more decimal places than you will ever need. It has always held. It held for Planck, who went looking for something that would still be true when nobody was here to say it, and found the 4 numbers that mark the place where the saying stops. It held for Bronstein for 31 years, and then it did not matter. It will hold for you, and underneath it, at a depth no instrument will ever reach, there is no flaw. There is not even a flaw missing, there is just the last place where the word down still meant something, and then the sentence ends.